Hello class, welcome to lecture 6, and in this lecture we're going to be covering the geostrophic wind, friction, and also some consequences of friction when we apply it to our definition of geostrophic wind. But first things first, we'll go ahead and get things started with the geostrophic wind. So geostrophic wind is defined as a force balance between the pressure gradient force and the Coriolis force. And by force balance, we mean that the two forces are exactly equal to each other in magnitude and also in opposite directions. So that means that the net acceleration and the net force that we're dealing with is in fact zero. Now, since we're only considering these two forces, that means we're going to be neglecting some forces as well. We're going to be neglecting centripetal force. So that means if you try to use this concept of geostrophic wind on curved flow, it's not going to work very well. In fact, if you want to account for centripetal and centrifugal force, you have to use something called the gradient wind, which will be a subject in next lecture. But for now, we're only going to worry about geostrophic wind, which is strictly a straight flow pattern. And the other thing about this balance is that it also neglects friction. So that means that this balance is not going to be valid wherever friction is significant. And as we'll see later on, the force of friction is quite strong once you get in the lowest 1 to 2, sometimes even the lowest 1 to 3 kilometers of the Earth's atmosphere. So geostrophic wind doesn't work very well in the lowest 1 to sometimes even 3 kilometers where friction is quite strong. But once you get above that, say above 700 millibars or roughly 3 kilometers above the ground, once you get above 700 millibars, then geostrophic wind does work pretty well because friction is usually not as significant. And sort of what just sort of summarize everything I just said to a good approximation, geostrophic wind, usually a pretty good representation of a straight flow pattern that is above 700 millibars. You can sometimes use geostrophic balance at lower elevations, but those are some pretty rare cases. Usually, if you're going to use geostrophic balance as a rule of thumb for what the wind should be, you want to restrict yourself to elevations that are above 700 millibars. So again, just to sort of reiterate a point that we mentioned earlier, that is by definition a force balance, which is what we're dealing with here. Geostrophic wind is by definition a force balance between the pressure gradient force and the Coriolis force. So that means the acceleration and the net force are both zero when we go to apply those to our equations of motions, which we got from Newton's second law. So again, just to remind you what those equations of motion look like. So since we're dealing with a force balance here, we can go ahead and state that the acceleration terms on the left-hand side, those are all zero. So we don't have to worry about any accelerating flow. And that's sort of a consequence that we'll have to keep in mind when we're working with geostrophic wind. That does in fact mean that our flow is not going to be, the speed is not going to be changing. The direction could be changing, but the speed, well actually no, the direction can't change because it's for straight flow, but the speed is not going to change and the direction is not going to change. So geostrophic wind does not accelerate at all. It does not change speed or direction. And also, when we go to use the geostrophic balance, we're going to primarily concern ourselves with the horizontal pressure gradient force. So we're not going to worry about the vertical component of the pressure gradient force, which also means we're not going to worry about the vertical component of the Coriolis force. So we're going to neglect this vertical component of the Coriolis force, and we're only going to focus on the pressure gradient force, which I'm sort of circling with the mouse cursor, and the Coriolis force, which I'm circling with the mouse cursor right now. And since we're only worried about the horizontal direction, we can neglect the entire z component. So we're only going to worry about the zonal and meridional components of the pressure gradient force and the Coriolis force. So I'm actually going to do this derivation simultaneously, simultaneously for both the standard surface, which is the 1 over, where the pressure gradient force is 1 over rho times f times the pressure gradient. And then also for an isobaric surface, which would be the geostrophic wind on a constant pressure level. So just to refresh your memory what that looks like, so on the standard surface we have 1 over rho times the pressure gradient, and if you want to, you can divide this f over to the left-hand side, so that's why I said 1 over f rho, and then this times, or this is all equal to k hat cross v, so minus 1 over rho gradient of pressure, again that's horizontal gradient, is equal to k hat cross v, and that's another way of writing the Coriolis force in vector form. And that's what this derivation is mostly going to center around, is doing this in vector form. And then once we get this in vector form, we can then break it down into components once we get an expression that we're pretty well pleased with. And then for a constant pressure surface or an isobaric surface, this is the expression for our pressure gradient force on an isobaric surface. That's just the minus gradient of the geopotential, and that's equal to Coriolis parameter times k hat cross v. And since we're solving for the wind, or trying to determine what the wind is, we want to solve for this v here. although there's something that makes that very unpleasant, and that is this k hat cross that is in front of the v here. So if we're going to solve for this v, we're going to have to find a way to get rid of this k hat cross in order to solve for our wind, which is represented by this vector v, and we're going to have to do that for both of these. Fortunately, there's a vector identity that we can use to make our lives a little bit easier, and that vector identity goes something like follows. If you k hat cross a vector twice, the result you get back from that is the negative of that vector. So for any vector represented by capital A, if I k hat cross that, then I get k hat cross A, and if I k hat cross this whole quantity, I get negative A. So if I k hat cross something twice, I get the negative of what I started with. So in this case, if I k hat cross the vector A, the result I get back is just negative A. So we can use that vector identity and k hat cross both sides of our equation up here. So we'll k hat cross our pressure gradient force and then k hat cross the right hand side, and then same thing over here for the isobaric case. So here we'll k hat cross the left hand side and also k hat cross the right hand side. And if we do that, we get a result that looks something like this. And then if we want to, we can take all the scalars, that is not the vector, those are the non-vector quantities, we can take all the scalars and pull those out in front so it's a little bit easier to work with. So we get minus 1 over rho k hat cross pressure gradient is equal to Coriolis parameter f k hat cross wind vector. And just using the identity that we have up here, this entire quantity on the right hand side, that is in fact now equal to minus v. And then same thing for the isobaric case. Except here we have k hat cross minus gradient and geopotential, that's equal to Coriolis parameter times k hat cross v, and just using the identity up here, k hat cross v just becomes minus v. So that's what we get after applying the vector identity that we have up here. And now we're actually in a position to solve for v. So to solve for v, we can just simply divide both sides by minus f, which is a Coriolis parameter, and this would be our final result. So our wind in geostrophic balance is equal to 1 over f times rho k hat cross gradient and pressure. And then similarly for the isobaric case, here we have the wind is equal to 1 over f. Notice we don't have density here. Again, that's another reason why the isobaric form of the pressure gradient forces is highly desirable, because you don't have to worry about density. But for a constant pressure surface, the wind would be 1 over Coriolis parameter times k hat cross the gradient and geopotential. So one thing that's often customary to do once you have this balance is to replace or to add this little subscript g to the vector that you get to sort of signify that this is in fact geostrophic wind. That's just something that's done mostly by convention. So this is just a sort of a nomenclature thing that just says now we have a wind that's in geostrophic balance, and that's defined as the equations that we have on the right hand side. The only change that was made from the previous slide to this one was the fact that we just added this subscript g here. And since we are working with the cross product, we can use the right-hand rule to sort of get sort of a bearing of what this geostrophic wind should look like if we're given information on the pressure gradient. Now, there's two ways you can sort of do this. The one I'm about to show you is the one I think is the simplest and easiest to remember. So one way you can evaluate a cross product using the right-hand rule is to have your thumb represent the first vector of the cross product, which is this k hat. And k hat's always going to point in the same direction. It's always going to point in the vertical direction. That is, it's always going to point straight upward. And then your index finger would then represent the pressure gradient, not the pressure gradient force, but the pressure gradient itself. Remember, those two vectors point opposite directions. Pressure gradient and pressure gradient force point opposite directions. Make sure you're pointing your index finger in the direction of the pressure gradient itself and not the pressure gradient force. And then if you're working isobaric coordinates, then you want your index finger to be pointing in the direction of the gradient and geopotential. And then if you do that, then the result that you get back will be your middle finger, which represents the direction of the geostrophic wind. So we'll see an example of this later on, but this is just one way that you can check to make sure that your answer makes sense if you're going to calculate geostrophic wind. So if you get a vector that's not pointing in the direction that the right-hand rule says it should be, then you know that you went wrong somewhere. So that's just sort of a way that you can check to make sure that you did in fact solve for the geostrophic wind correctly. It's just to use this quick and easy right-hand rule. And if we want to, we can break this down to component form. And to do that, we would have to evaluate this cross product, which, yeah, that's a lot of fun. I know, to evaluate cross products, can't get enough of it. But this cross product, in this case, this cross product is kind of easy to evaluate, easier than other cross products, if there is such a thing. So here is just, the first vector is just one unit in the k-hat direction. So that's just 0, 0, 1. And then here we're only worried about the pressure gradient, the horizontal pressure gradient. So that's dp dx, dp dy, and then the vertical term is just 0. And then we can pull the scalars out in front. And if we go to evaluate that cross product, we get a result that looks like this. So relatively simple for cross product standards. And if we want to, we can also rewrite the left-hand side, this geostrophic wind vector, in its own component form. So here I'm using U sub g to represent the zonal component of the geostrophic wind, that is the component that runs in the east-west direction, and I'm using V sub g without the vector symbol over it to represent the meridional component of the geostrophic wind, that is a component that runs in the north-south direction. And one of the basic rules of vectors is that each individual component has to be equal to each other. So that means that whatever's in the I-hat component on the left-hand side must be equal to whatever's in the I-hat component on the right-hand side. And then same thing for the J-hat component. Whatever is part of the J-hat component on the left-hand side, the equal sign must be equal to whatever's in the J-hat component on the right-hand side. And since the K-hat is 0, there's no vertical component, then there's no vertical component of geostrophic wind. So geostrophic wind is purely horizontal, or I probably should say quasi-horizontal. There's no vertical component to speak of. And if you want to write the individual components out, then you get that the zonal component of geostrophic wind is equal to minus 1 over Coriolis parameter f times density rho times the meridional pressure gradient, that is dp dy. And then the meridional component of the geostrophic wind is equal to 1 over, notice there's no negative sign here, the meridional component is equal to 1 over Coriolis parameter f times density rho times the zonal gradient in pressure, or dp dx. And if we want to, we can do this for the definition in the isobaric coordinates, where we're on a constant pressure surface. Very much the same process, just another cross product. Not a whole lot changes here, actually. Just the main thing that changes is the fact that we don't have density and we're working with geopotential gradient instead of pressure gradient. So again, if we evaluate that cross product, we get a result like this. And just like before, whatever is in the I-hat on the left-hand side must be equal to the I-hat on the right-hand side. So that means the zonal component of the geostrophic wind must be equal to minus 1 over f times d phi dy. And then whatever's in front of the j-hat on the left-hand side must be equal to whatever's in front of the j-hat on the right-hand side. So that would mean we have Vg equals 1 over f times d phi dx. And again, no vertical component in the geostrophic wind. And then if we separate those components out, we get that the zonal component of the geostrophic wind is equal to minus 1 over the Coriolis parameter f times the geopotential gradient in the meridional direction, or d phi dy. And then the meridional component of the geostrophic wind, that'll be equal to 1 over the Coriolis parameter times the zonal gradient of the geopotential. So that's just 1 over f times d phi dx. So that's going to do it for the derivation of the geostrophic wind. In the next segment, we'll take a look at some questions and an exercise to sort of check your understanding, make sure that you're up to speed. So with that, I will see you all in the next segment.